The morning of March 25, 1945, Captain Robert Morgan settled into the left seat of his B-29 Superfortress, call sign Dauntless Dottie, and began the pre-flight checklist that would take his crew higher than any bomber formation had ever attacked from. The briefing that morning had been explicit. Target altitude, 32,000 feet, 4 miles straight up, higher than Mount Everest's base camp. An altitude where the air is so thin that exposed human blood boils at body temperature. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The order seemed insane to crews who'd been bombing Japan from 25,000 feet for months. But American commanders had discovered something extraordinary through brutal trial and error. At 32,000 feet, Japanese fighters simply couldn't reach them. Not wouldn't, couldn't. The physics of altitude, engine performance, and atmospheric density had created an invisible ceiling that turned America's most advanced bomber into something approaching invulnerable. This wasn't the war planners had envisioned. This was desperation transformed into doctrine through careful observation of what actually worked versus what was supposed to work. And the story of how American crews discovered this aerial sanctuary reveals a collision between Japanese engineering limitations and American technological advantages that would help decide the Pacific War. The problem started becoming apparent in late 1944. B-29 seconds, flying from newly captured bases in the Mariana Islands, were hitting Japanese targets from altitudes around 25,000 feet, exactly as doctrine prescribed. American strategic bombing theory, developed through years of European operations, emphasized high-altitude precision bombing. Fly high enough to avoid most anti-aircraft fire, use the Norden bomb site to hit specific industrial targets, avoid civilian casualties when possible. The theory was sound. The execution in the Pacific revealed complications nobody had anticipated. Japanese fighters were reaching B-29 formations at 25,000 feet with alarming regularity. The Mitsubishi A-6M0, famous for its agility at lower altitudes, struggled above 20,000 feet, but Japan had developed high-altitude interceptors specifically to counter B-29 raids. The Kawasaki Ki-61 Tony could reach 26,000 feet. The Nakajima Ki-84 Frank could hit 28,000 feet in optimal conditions. Most dangerous was the Mitsubishi J-2M Raiden, codenamed Jack by Allied intelligence. This interceptor was designed from the outset for high-altitude bomber interception. Powered by a Mitsubishi Kasei engine producing 1,800 horsepower, optimized for thin air performance, the Jack could reach 30,000 feet under ideal circumstances. Japanese pilots flying these aircraft were skilled, determined, and absolutely willing to die taking a B-29 with them. They'd developed tactics specifically for attacking the massive American bombers. Single-engine fighters would climb laboriously to altitude, conserving fuel and energy. They'd position themselves above and ahead of the bomber formations, then dive through at high speed, firing 20mm cannon and 13mm machine guns at the B-29's wings and engines. Even if they didn't destroy the bomber outright, battle damage forced aircraft to drop out of formation, where they became vulnerable to follow-up attacks. The numbers told a grim story. In December 1944, the 21st Bomber Command, operating B-29 seconds from the Marianas, was losing approximately 3% of aircraft per mission to all causes. That included mechanical failures, anti-aircraft fire, and fighter attacks. 3% sounds manageable until you calculate the mathematics of survival. A bomber crew flying 30 missions had roughly a 60% chance of being killed or captured. Those odds were barely better than coin flips repeated until someone lost. Worse, the bombing results weren't justifying the losses. High-altitude precision bombing required clear visibility of the target. Japan's weather, particularly during winter months, meant cloud cover obscured targets on more than half of all missions. Bombers would fly 7 hours from the Marianas, climb to 25,000 feet, approach Tokyo or Osaka or Nagoya, and discover solid cloud decks hiding the entire city. They'd drop bombs through clouds using radar, hitting nothing of strategic value, then fly 7 hours back having accomplished nothing except putting themselves at risk. Major General Curtis LeMay took command of 21st Bomber Command in January 1945 with orders to make the B-29 campaign effective. LeMay was brutally pragmatic. He looked at loss rates, bombing accuracy, and strategic results, with the cold calculation of an engineer analyzing failed systems. What he saw was a bombing campaign that was hemorrhaging crews and aircraft while barely impacting Japanese industrial capacity. The altitude question became central to LeMay's analysis. Every 1,000 feet of altitude provided advantages and disadvantages. Higher altitude meant thinner air, which reduced anti-aircraft shell effectiveness because shells lost velocity faster in thin air. Higher altitude meant fewer Japanese fighters could reach you because aircraft engines lose power as air density decreases. But higher altitude also meant lower bombing accuracy because bombs had farther to fall, giving wind more time to push them off course. And higher altitude meant aircraft systems operated at the extreme edge of their design parameters. LeMay's operations research analysts began compiling data from every mission flown since November 1944. They tracked altitude, weather, fighter encounters, bombing, accuracy, and aircraft losses. Patterns emerged. Missions flown above 28,000 feet experienced significantly fewer fighter attacks. Japanese interceptors that did reach those altitudes were struggling. Their rate of climb slowed dramatically above 25,000 feet. Their maneuverability degraded. Their guns fired less effectively in the thin air. The physics were immutable. An aircraft engine is essentially an air pump. It sucks in air, mixes it with fuel, ignites the mixture, and uses the expanding gases to produce power. At sea level, air contains approximately 14.7 pounds per square inch of pressure. At 25,000 feet, that drops to 5.5 pounds per square inch. At 30,000 feet, only 4.3 pounds per square inch. Aircraft engines produce power proportional to air density. Less air equals less power. Japanese aircraft engines, optimized for carrier operations and lower altitude combat, where most Pacific fighting occurred, lost power dramatically at extreme altitude. The Mitsubishi Kasei engine in the JAC Interceptor was rated at 1,800 horsepower at sea level. At 30,000 feet, that same engine produced perhaps 900 horsepower, half its rated output. The Zero's Nakajima Sake engine, producing about 1,000 horsepower at sea level, managed perhaps 500 horsepower at 30,000 feet. American B-29 engines used turbochargers, specifically designed for high-altitude performance. The Wright R-3000, 350, duplex cyclone, producing 2,200 horsepower at sea level, maintained over 1,500 horsepower at 30,000 feet through turbocharging. This wasn't a minor advantage. This was the difference between an aircraft that could barely maintain altitude versus an aircraft that could still climb and maneuver effectively. The turbocharger was fundamentally a clever piece of engineering that used waste exhaust gases to compress intake air, maintaining higher air density for the engine even as external air density dropped. General Electric had developed turbochargers for aircraft applications in the 1930s. By 1944, the technology was mature, reliable, and gave American high-altitude aircraft a decisive advantage. Japanese engineers understood turbocharging. They'd attempted to develop similar systems. But Japan's industrial capacity, already strained by years of war, couldn't manufacture turbochargers at scale with adequate reliability. The precision machining required, the heat-resistant alloys needed, the tight tolerances demanded, all exceeded what Japanese factories could consistently produce. So Japanese fighters flew with conventional superchargers that provided some altitude capability, but nothing approaching American turbocharger performance. The operational ceiling, the maximum altitude where an aircraft can still climb at least 100 feet per minute, told the story starkly. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The B-29's operational ceiling was 36,000 feet in standard conditions. The Mitsubishi Jack's operational ceiling was 32,800 feet under optimal conditions, with a light fuel load and experienced pilot. The Kawasaki Tony maxed out around 30,000 feet. The famous Zero couldn't effectively operate above 25,000 feet, but those were theoretical numbers, achieved in test conditions with new aircraft, expert pilots, and perfect maintenance. Combat conditions were never optimal. Aircraft engines wore down, pilots of varying skill flew missions, fuel loads reduced performance. Most critically, climbing to maximum altitude burned enormous quantities of fuel. A Japanese interceptor climbing from sea level to 30,000 feet consumed roughly half its total fuel capacity in the climb alone. Fighter tactics require fuel reserves for combat maneuvering. Dogfighting, tight turns, rapid acceleration, all consumed fuel rapidly. If Japanese pilot burned half his fuel just reaching B-29 altitude, he had perhaps 15 minutes of combat time before fuel state forced him to disengage and descend. 15 minutes wasn't much time to locate a formation of bombers in three-dimensional space, position for attack, make attack runs, and achieve results. American intelligence knew this. Captured Japanese pilots, interrogated after being shot down, provided detailed information about their aircraft's capabilities and limitations. They described the desperate struggle to reach B-29 formations, how their aircraft wallowed in thin air, controls feeling mushy and unresponsive, how closing speeds were so high they had only seconds to aim and fire before flashing past the target, how their guns, designed for lower altitude combat, experienced reduced muzzle velocity and accuracy in the thin atmosphere. One captured Japanese pilot, First Lieutenant Sadamu Komachi, shot down over Iwo Jima in February 1945, described intercepting B-29 seconds as attempting to catch lightning while carrying stones. His aircraft felt impossibly heavy at altitude. The Americans seemed to float effortlessly while Japanese fighters clawed for every foot of altitude. By the time he reached the bomber formation, his aircraft was practically stalling, controls barely responsive, while the B-29 seconds maintained formation speed that seemed impossible for such large aircraft. The B-29's speed advantage at altitude was another factor Japanese pilots hadn't anticipated. At 30,000 feet, a B-29 cruised at approximately 330 miles per hour indicated airspeed. True airspeed, accounting for thinner air, was closer to 420 miles per hour. Japanese fighters at that altitude were near their maximum speed, just keeping up. They had little excess speed for maneuvering or attack runs. Closing speed dictated combat geometry. If a Japanese fighter approached from behind, attempting a tail attack, the relative closing speed might be only 50 miles per hour. At that speed, the fighter had perhaps 30 seconds of firing opportunity before either overshooting or running out of ammunition. If the fighter attempted a head-on pass, closing speed exceeded 700 miles per hour. The fighter pilot had perhaps 2 seconds to aim and fire before the B-29 flashed past. 2 seconds, while dealing with thin air, sluggish controls, and guns that might not fire reliably at that altitude. The B-29's defensive armament made these attacks even more difficult. The Central Fire Control System, revolutionary when Boeing designed it in 1940, gave American gunners enormous advantages. A gunner sitting comfortably in a pressurized compartment, using computing gun sights that automatically calculated lead angles, could engage fighters with accuracy that seemed impossible to Japanese pilots accustomed to attacking bombers with manual gun positions. The 4 remote-controlled turrets, each mounting twin 50-caliber machine guns, provided overlapping fields of fire. A Japanese fighter making an attack run might face fire from multiple turrets simultaneously. The 50-caliber rounds, while lighter than Japanese 20mm cannon shells, had excellent ballistic characteristics and high muzzle velocity. A single 50-caliber round striking an engine could cause catastrophic damage. Several hits to cockpit or fuel tanks meant certain death. By February 1945, LeMay's analysts had compiled enough data to make recommendations. Missions flown above 30,000 feet experienced approximately 70% fewer fighter attacks than missions at 25,000 feet. Of the fighter attacks that did occur above 30,000 feet, success rates were roughly 40% lower. Japanese fighters struggled to maintain altitude, maneuver effectively, and press attacks home with determination. The numbers were stark. At 25,000 feet, approximately 11% of B-29 seconds per mission experienced fighter attacks, resulting in battle damage. At 30,000 feet, that dropped to 4%. At 32,000 feet, it fell to less than 2%. The statistical advantage was overwhelming. Fly 4 miles high, and you'd transformed Japanese fighters from a critical threat into an occasional nuisance. But flying at 32,000 feet created new problems. The Norden bombsight, designed for precision bombing from 20,000 to 25,000 feet, lost significant accuracy at higher altitudes. Bombs dropped from 32,000 feet fell for approximately 45 seconds before impact. During that time, prevailing winds at multiple altitudes pushed bombs off course. Crosswinds at 30,000 feet might be completely different from winds at 20,000 or 10,000 feet. Calculating accurate bombing solutions required understanding wind conditions at multiple altitude layers, data that was difficult to obtain and constantly changing. Test drops conducted at Wendover Field in Utah during January 1945 demonstrated the problem. From 32,000 feet, even in calm conditions with expert bombardiers, circular error probability, the radius within which 50% of bombs fell, exceeded 800 feet. From 25,000 feet, that error was closer to 400 feet. Doubling the altitude roughly doubled the margin of error. For precision strategic bombing, hitting specific factory buildings or rail yards, 800-foot error margins made accuracy nearly impossible. But LeMay was already questioning whether precision bombing was the right doctrine for Japan. Japanese industry was dispersed, not concentrated in large factories like German production. Small workshops throughout residential areas manufactured aircraft components, weapons parts, and military supplies. Destroying Japanese industrial capacity might require destroying entire urban areas, not surgical strikes against specific buildings. That thinking would lead to the controversial low-altitude incendiary bombing campaigns in March 1945. But for daylight precision raids that continued throughout the spring of 1945, the altitude question remained critical. If crews were going to fly high-altitude missions, they might as well fly at altitudes where Japanese fighters genuinely couldn't reach them, even if bombing accuracy suffered. The decision came down in early March. Standard operational altitude for daylight precision bombing missions would be 32,000 feet, weather and conditions permitting. Crews received updated procedures for high-altitude operations. Bombardiers trained with new sight settings and wind calculation methods. Pilots practiced sustained flight at altitudes, where engine temperatures ran cooler, but control responses became sluggish. The first missions at 32,000 feet revealed what the analyst reports had predicted. Japanese fighters appeared, climbing desperately toward the American formations. Some reached 28,000 feet. A few particularly determined pilots in well-maintained aircraft reached 30,000, but at that altitude they were barely flying. Their aircraft were near stall speed. Control surfaces felt like they were moving through mud. Making aggressive maneuvering attacks was essentially impossible. American gunners watched Japanese fighters climb toward them, then fall away as the fighters ran out of altitude capability or fuel reserves. Some Japanese pilots, frustrated by their inability to reach the bombers, would roll inverted and dive away, abandoning the interception attempt. Others tried climbing in wide spirals, attempting to gain just a few more 100 feet, but the mathematics of engine power and air density made it impossible. Captain Morgan's crew, flying Dauntless Dottie, on that March 25th mission, experienced the new doctrine firsthand. They climbed to 32,000 feet en route to the target, a Mitsubishi aircraft engine factory near Nagoya. The climb took 40 minutes of sustained power settings that made engineers nervous about engine temperatures, but once level at altitude, the aircraft settled into cruise configuration. Indicated airspeed showed 210 miles per hour. True airspeed was 390 miles per hour. They were covering ground faster than most fighters could fly at sea level. Japanese fighters appeared as they approached the target area. At first, they were just dark specks against clouds far below. Then some of those specks began climbing. Morgan counted 6 fighters attempting interception. His gunners called out bearings and ranges. The central fire control system automatically trained turrets toward the threats. But the threats never materialized into actual danger. The Japanese fighters climbed to perhaps 28,000 feet. At that altitude, still 4,000 feet below the B-29 formation, they leveled off. Morgan could see them through his cockpit window, dark shapes wallowing in thin air, unable to climb higher. One fighter attempted a long-range firing pass, shooting at the formation from below with little chance of hitting anything. The .50 caliber rounds reached the altitude easily, but the fighters didn't. After roughly 5 minutes of futile attempts, the Japanese pilots gave up and spiraled back toward lower altitudes where their aircraft could actually maneuver. The bomb run proceeded without fighter interference. Anti-aircraft fire proved ineffective at 32,000 feet. Japanese anti-aircraft guns, primarily 88mm and 127mm weapons, could reach that altitude, but shell fragmentation lost effectiveness in thin air. Shells that would create lethal fragments at 20,000 feet produced harmless puffs of black smoke at 32,000 feet. The shrapnel simply didn't have enough air density to maintain velocity and lethality. Morgan's bombardier, Lieutenant James Carlson, made his bombing run using updated sight settings for extreme altitude. The target appeared small and indistinct through the northern sight, just geometric shapes that might be factory buildings. Carlson tracked the aim point, adjusted for calculated wind, and released the bomb load. 12 500-pound general-purpose bombs fell away in sequence. The aircraft lurched upward slightly as 6,000 pounds of weight departed. 43 seconds later, the bombs impacted. From 32,000 feet, visual confirmation of hits was nearly impossible. Carlson thought he saw explosions in the target area, but couldn't confirm accuracy. Post-mission reconnaissance photos would show that roughly 30% of the bombs landed within the factory complex, an acceptable hit rate for extreme altitude bombing. More importantly, every aircraft in the formation returned safely. 0 losses to fighters, 0 losses to anti-aircraft fire. All battle damage was minor. That became the pattern throughout March and April 1945. Missions flown at 32,000 feet experienced dramatically lower loss rates than earlier operations. Japanese fighters continued attempting interceptions, but physical laws prevented success. The few fighters that did reach anywhere near B-29 altitude were operating at the absolute edge of their performance envelope. Their pilots, already dealing with oxygen deprivation despite oxygen masks, struggled with aircraft that barely responded to control inputs. Japanese pilots began reporting that intercepting B-29 seconds at extreme altitude was nearly suicidal, not because of American defensive fire, but because the attempt itself was so dangerous. Aircraft would flame out at altitude when engines couldn't maintain combustion in thin air. Controls would lock up from reduced air pressure on control surfaces. Pilots would black out from oxygen deprivation when oxygen systems failed under strain. Several Japanese interceptors were lost simply from attempting to reach B-29 formations at altitudes their aircraft couldn't safely operate. The Japanese Army Air Force and Naval Air Service tried adapting tactics. They experimented with interceptors carrying external drop tanks for extended climbing time. They tried having fighters launch from bases already at altitude, like airfields in mountainous regions, to reduce the climb distance. They attempted coordinated attacks where multiple fighters would climb together, hoping that if 1 or 2 reached the bombers, the casualties might be acceptable. None of it worked. The fundamental physics couldn't be overcome through tactics. Japanese aircraft engines, lacking effective turbocharging, simply couldn't produce enough power at extreme altitude. And even when individual aircraft reached 30,000 feet, they had no combat capability remaining. They were barely flying, let alone fighting. American intelligence officers documented this through multiple sources. Intercepted Japanese radio communications revealed pilot frustration. One transmission, intercepted and translated in April 1945, had a Japanese pilot reporting to his base commander that reaching the American bombers was impossible that his aircraft was shaking violently at altitude, and that his guns wouldn't fire reliably. The base commander ordered him to try again anyway. The pilot acknowledged the order, then was never heard from again. His aircraft presumably crashed or he was killed attempting the impossible. Captured documents from Japanese air bases revealed the toll. One flight group based near Tokyo reported that of 42 interception attempts against high-altitude B-29 formations in March 1945, only 7 fighters reached anywhere near bombing altitude. Of those 7, none successfully damaged a B-29. 3 fighters were lost in the attempts, not from American fire, but from mechanical failures or pilot incapacitation at extreme altitude. The Japanese attempted one final solution: specialized high-altitude interceptors designed specifically for B-29 combat. The Tachikawa Ki-94, a purpose-built high-altitude fighter, was under development with a service ceiling projected at 40,000 feet, but the aircraft never entered production before war's end. Japan's industrial capacity was collapsing under sustained American bombing. Factories that might have built advanced interceptors were being destroyed faster than new ones could be completed. The altitude advantage fundamentally shifted the strategic balance. B-29 crews, flying at 32,000 feet, operated in relative safety. Loss rates dropped from 3% per mission to less than 1%. Crew morale improved dramatically. The statistical chances of completing a combat tour and returning home increased substantially. Men who'd been flying missions with grim fatalism began believing they might actually survive the war. The bombing campaign's effectiveness remained debated. High-altitude precision bombing from 32,000 feet never achieved the accuracy pre-war doctrine promised. Most missions destroyed only a fraction of their intended targets. But the psychological impact on Japanese defenders was significant. American bombers appeared overhead almost daily, flying at altitudes Japanese forces couldn't reach, dropping bombs with impunity, and departing unscathed. The message was clear. American air superiority was total and unchallenged. Japanese civilians, watching contrails from B-29 formations crossing overhead at extreme altitude, understood their own air forces couldn't protect them. The silver aircraft left white trails across clear skies, geometric patterns of contrails from 4 engines per aircraft, dozens of aircraft per formation, formations that Japanese fighters couldn't reach and anti-aircraft guns couldn't hit. It was visible proof that Japan had lost control of its own airspace. The technical achievement represented in those missions was extraordinary. Boeing's engineers, working under impossible timelines in 1940 through 1942, had designed pressurization systems that allowed human beings to operate comfortably at altitudes that would kill them in seconds without protection. The Wright engineers who developed the R-3350 engine had created power plants that maintained performance at altitudes where Japanese engines gasped for air. General Electric's turbocharger designers had given American aircraft decisive altitude advantages. But perhaps more importantly, American operational commanders had been willing to abandon cherished doctrine when evidence showed it didn't work. Pre-war strategic bombing theory emphasized precision from moderate altitudes. When combat experience revealed that moderate altitude over Japan meant unacceptable losses, commanders adapted. They pushed operations to extreme altitudes where aircraft performance advantages became overwhelming, even though bombing accuracy suffered. The Japanese couldn't make similar adaptations. Their industrial base couldn't produce turbochargers at scale. Their engineering programs couldn't develop high-altitude interceptors fast enough. Their tactical doctrine, emphasizing agility and maneuverability at lower altitudes, proved irrelevant when combat moved above 30,000 feet. They were trapped by technological and industrial limitations that no amount of pilot courage could overcome. By May 1945, the pattern was established. Daylight precision bombing missions operated at 32,000 feet as standard procedure. Japanese fighter interceptions had become so rare that some crews completed entire combat tours without ever firing their defensive guns at an enemy aircraft. The invisible ceiling, created by atmospheric physics and engine technology, had transformed the B-29 from a vulnerable bomber into an aircraft that operated beyond enemy reach. Captain Morgan's crew completed their combat tour in June 1945. They'd flown 34 missions, all at extreme altitude, all without serious battle damage from fighters. Morgan later wrote that the most dangerous part of each mission wasn't Japanese defenses. It was the mechanical stress on aircraft systems from sustained operations at 32,000 feet. Engines ran hot despite thin, cold air. Pressurization systems strained to maintain cabin pressure. Turbos occasionally failed, forcing aircraft to descend to lower altitudes where they became vulnerable. But compared to earlier operations at 25,000 feet, the altitude advantage was life-saving. Morgan calculated that flying at 32,000 feet probably reduced his crew's chance of being killed or captured by at least 60% compared to flying at conventional bombing altitudes. That 60% difference meant hundreds of American air crew members survived, who would have died operating at lower altitudes. The irony wasn't lost on anyone involved. America's most advanced bomber, designed for precision strategic bombing, achieved its greatest success not through precision, but through flying so high that enemies couldn't reach it. The technology that made this possible, pressurized crew compartments and turbocharged engines, had been developed to enable precision bombing. Instead, it enabled survival through altitude advantage. Japanese engineers and military leaders understood exactly what had happened. Post-war interrogations of Japanese aviation officials revealed they'd recognized the altitude problem as early as late 1944, but recognition didn't equal solution. Japan lacked the industrial capacity, raw materials, and time needed to develop countermeasures. American bombing had disrupted Japanese aircraft production too severely. Fuel shortages, limited training for pilots. By the time Japanese engineers designed high-altitude interceptors, there were no factories remaining capable of building them in meaningful numbers. The B-29 missions at 32,000 feet represented a convergence of technological advantage, industrial capacity, and tactical adaptation. American engineers had designed systems that worked at extreme altitude. American factories had built thousands of engines and aircraft incorporating those systems. American commanders had been willing to modify tactics when evidence demanded changes, and American crews had operated those aircraft at the absolute edge of their performance envelope because doing so kept them alive. The visible result was contrails across Japanese skies that Japanese fighters couldn't reach. The invisible result was a strategic bombing campaign that continued unabated until Japan surrendered. Not because American-Japanese bombing was devastatingly accurate, it wasn't, but because American bombers operated beyond Japanese ability to effectively counter them. The altitude advantage, created by turbochargers and pressurization, made the difference between a bomber campaign that might have failed and one that succeeded through sheer operational sustainability. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.